In this session, we're going to take a basic look at what VPNs are, and then what IPsec VPNs are, and then we're going to go to the actual configuration of a very simple IPsec VPN between the ASA and the iOS. But again, at the CCNA level, we're just going to have a basic, fundamental, very basic level touch with the technology, because otherwise IPsec VPNs it's a huge technology by itself. So before going to explaining what IPsec VPNs are, let's see what VPNs are by themselves. So a VPN stands for a virtual private network, which what that means, it's a private network, which means it belongs to a company. But because that network is going to be connected over some kind of open network like the internet, it means you're going to have some kind of virtual connectivity in between. Like for example, if you want to provide connectivity between two sites of your company, or between a remote office and the headquarters, or between a remote user working from internet cafe and the headquarters, because you're not going to have a dedicated lease line in there, you need some kind of virtual connectivity so that the users or those two sites can communicate in between over whatever the type of connection is in between. So VPNs don't necessarily imply security, which security means CIA, so confidentiality, integrity, and authentication. It just means that the connection is not physical. So between those two sites, or between that remote user and the headquarters, you don't have a long cable or a dedicated lease line, but rather you have a logical connection in there. So a couple of VPN examples. We have either layer 2 VPNs, which even an Ethernet VLAN, or frame rate PVC, or ATM PVC, or an MPLS layer 2 VPN, Atom VPLS, ELAN, whatever the type of layer 2 VPN is, that is a VPN in the end. Because those technologies allow you to connect, two different sites to those two sites are going to show up as connected at layer 2, but actually in between those two sites you have a lot of devices in between layer 3 devices or layer 2 devices that provide a end-to-end connectivity of type layer 2. So it's not an end-to-end cable between those two sites of yours. Likewise, we have layer 3 VPNs, which means you're going to connect those two sites of yours via layer 3 connection, which some examples could be MPLS layer 2 VPNs, GRV tunneling, IP and IP tunneling, and of course IPsec and SSL tunneling, which those kinds of connections actually imply security, IPsec and SSL. So now, what is IPsec? Again, the name says exactly what it's going to do. It's IPsec, stands for IP security. So it's a framework which defines how can we provide secure VPN connectivity for IPv4 and IPv6 based networks between those two sites of our company, or those 100 sites of our company, or between a remote user working from internet cafe and the headquarters. So it's a VPN connection with a specific scope to add IP security, to the IP traffic in between those sites. So it's going to be, because it's a framework, it's lots of open standards. Here I only couple of them, probably it's 3, 4, 5 times more than this. But most important, I'm going to speak about a couple of them in the presentation. It's going to be RFC 2408, which is the ISACAM RFC, 2409, which is the IKE RFC, 7296 is going to be IV2 RFC, 4301, Security Architecture for the Internet Protocol, 4302, IP Authentication Header, and 03D IP Encapsulating Security Payload, or ESP. Now when we want to provide that secure connectivity for the IP traffic, we have a couple of IPsec VPN types. So we have site-to-site or remote access, where site-to-site VPN is usually between two VPN gateways, or at least one needs a static or known IP address. Where remote access VPN is going to be usually between a user or a device or a very small remote office and a centralized VPN gateway, where usually the user or the device has a dynamic IP address. So like if you look at our diagram in here, For example, assuming that on the left side in here and on the right side in there, you have those are your two sites. On the left side, we have site A of our company, site A, and on the right side, site B. And you can see traffic to send traffic back and forth between those sites. We travel to this unsecure network. Can be whatever, the internet, MPLS, doesn't matter what kind of connection is in there. So we want traffic to travel in between those sites securely via an IPsec VPN. So because this is between two sites of our company, it's going to be a site-to-site VPN. So we're going to build up a VPN between, for example, this device and this device. We're going to fire up a IPsec VPN tunnel. It's going to be site to site. And of course, for the IPsec VPN tunnel to be established, at least one of those two VPN gateway needs a known or static IP address. Of course, you can also build up the VPN based on fully qualified domain names, which means it's going to allow the IP addresses to change back and forth because I'm going to resolve the name to whatever the IP address is at that point. But in general, in most cases, the site-to-site IPsec VPN is going to be between two VPN gateways, where usually both of them are statically assigned IP addresses, but it can also work with one of them being dynamically assigned, and very rarely you're going to see both of them having dynamic IP addresses in there. And remote access is going to be like, for example, those are our sites in there, and let's assume that this transport network will be the internet, for example. This is going to be the internet. And you have one user which is in the internet in here, the user, and he also wants to securely send traffic to either site A or site B, which means that user is going to build up another IPsec VPN tunnel with either this VPN gateway or the other VPN gateway. And because the user usually is, you know, in the airport, in an internet cafe, in, you know, at a Starbucks or whatever, doesn't matter, it means that usually is going to have a dynamic IP address in there. But a VPN gateway is going to have usually a fixed IP address in most cases. Now, so let's see what are the security features that IPsec can add for IP traffic, IPv4 or IPv6. So you need to make sure that it provides origin authentication. So when the VPN tunnel is being built, we need to make sure that as packets flow through that IPsec VPN tunnel, we authenticate the source. We want to make sure that the packet came in from the remote user or from the remote site of ours. We don't want anybody to be able to inject spoofed packets in there. Data integrity, which means you got to make sure that the data was not modified in transit unauthorized. Data confidentiality, so nobody in the transit path, like in the internet, if they manage to capture the traffic, it means that we don't want them to be able to read the data. Anti-replay, which means this is against some kind of attacks where somebody could, you know, maliciously send replay packets in the tunnel to confuse the VPN gateways or to, you know, bring down the tunnel, for example. So you got to make sure that the IPsec provides anti-replay functionality for the protected IP traffic. And of course, most importantly as well in there, because what we spoke so far is only for the data plane traffic or traffic injected in the VPN, in the IPsec VPN tunnel. But of course, to provide all of those functions like data, origin authentication, integrity, and confidentiality, which means encryption and hashing and private public key, whatever we're going to speak about next, to provide all of those features, it means that we need some kind of the VPN gateways or the remote user and the VPN gateway need to somehow end up with some secure keys to encrypt the traffic, to use as the seed input value in the hashed base, in the HMAC version of the hashing algorithms. So the two parties need to end up with some secure keys back and forth that are going to use to encrypt traffic and hash traffic and whatever we also discussed in the cryptography in the cryptography section. So for that to happen, IPsec also needs a key management framework so that those two IPsec VPN peers securely negotiate the keying material used to secure the packets over the non-secure transport, which is the internet, and provide all of those features: authentication, integrity, and confidentiality. So let's speak about in more details about all of those IPsec security features. Just as a reminder, so when we build up the tunnel, the IPsec VPN tunnel, the origin or the peer authentication, because when the VPN tunnel is being built, the IPsec VPN tunnel, the peers, the VPN gateways need to authenticate in between. It's going to be a bidirectional authentication. So for that we can use either pre-secure authentication, we can use RSA signatures, we can use elliptic curve DSA signatures, or we can use RSA encrypted nonces, which is going to be nothing else but RSA keys, but also combined with random numbers. While the RSA signature is going to be digital certificates. So RSA signatures means using digital certificates. RSA encrypted nonsense means just a basic private public key pair alongside with random numbers. Usually the most commonly seen are going to be the pre-share keys and RSA signatures and ECDSA signatures, but RSA encrypted nonsense is not really deployed on a large scale. To provide data integrity, clearly is going to be hashing, but the keyed hash MAC version, which means when I'm going to perform hashing, I'm going to put in the hashing algorithm not only the data packet, but also a secure key, which is going to be known by the VPN gateways. And of course, the well-known hashing algorithms, MD5, SHA-1, or SHA-2. Data confidentiality, which means encryption, we're going to make use of the well-known protocols, DES, triple DES, or AES. Now, anti-replay, depending on the IPsec VPN tunnel type, it can be done either based on is going to be either counter-based, which means all packets sending the VPN tunnel are going to be using sequence numbers to make sure that we know what is the next sequence number of the next packet we should expect to receive in the IPsec VPN tunnel, or it can be time-based. Most IPsec VPN tunnels are going to be using a counter-based anti-replay functionality. And of course now the key management, so how do those VPN gateways end up with the same keying material securely? We're going to make use of either IKE or IKE v2, which that's another kind of like a framework which defines the negotiation of IPsec tunnel and the encryption keys or the secure keys, because IKE and IKE v2 don't only negotiate the encryption keys, but also the other kind of keys in there. So IKE and IKE v2 are going to define it's going to be two different frameworks which define the negotiation of the tunnel and how the keying material is derived securely between the VPN gateways. And within IKE or IKE v2, we have another another algorithm, which is going to be a private public key algorithm, the Diffie-Hellman algorithm, which is the magic protocol. We're going to speak about it briefly. It is the magic algorithm, asymmetric algorithm, which allows the two VPN peers to derive a common shared secret key without the need to exchange it. So what's going to happen is we're going to see in a couple, when the VPN gateways run the Diffie-Hellman exchange, they're going to send some values back and forward in clear text, and then both VPN peers magically, of course not magically, via a mathematical algorithm, end up with a common secure key without actually sending that key over the wire, because that would break the whole security of the IPsec VPN tunnel if we would send the negotiated secure key in clear text to be visible and captured by anybody in the transit path. Now more on the key management. So as I said, IKE and IKE v2 are frameworks, but actually the framework which defined how to negotiate the keying material, it's based on multiple, let's say, mathematical schemes. So ISACAMP defines a framework for authentication and key exchange. Oakley defines a series of key exchanges. and scheme defines techniques for key exchanges. You might say, why is this so complicated? Because those, let's say, algorithms or those documents, those standards, to call it simpler, were not only defined, in the for the scope of IPsec. So those were only, definitions of in case two peers need to negotiate some key material, how should they do that, and what are the options to perform the key exchange. So that's only like the theory part. But the actual implementation of IPsec VPN for key management uses IKE or IKEv2. So IKE or IKEv2 combine ISACAMP, Oakley, and Scheme and define exactly how keys should be generated for IPsec VPNs. Because ISACAMP, Oakley, and Scheme were pretty much opened, and since we want to have inter-vendor operability to run an IPsec VPN tunnel, we need to tell everybody how the key management negotiation process should happen and exactly how that should happen, because otherwise you're not going to be able to run an IPsec VPN tunnel between a CISCO device and other vendor devices, a Juniper, Fortinet, whatever, doesn't matter. And of course, for the both IKE and IKEv2 serve the same goal, which it is to so that the VPN gateways know how to negotiate the key material back and forth, those secure keys used to secure the IPsec VPN tunnel. But behind the scenes, they work differently. So IKE and IKEv2 are not backwards compatible. Now, of course, initially we had IKE, and then IKEv2 showed up. So why they are not backwards compatible? Because IKEv2 was created to overcome some limitations of IKE, and not only limitations, but also, let's say, some design flows to keep it simple. But that's a more advanced topic. So that's why they couldn't make IKEv2 to be backwards compatible with IKE, because it would break the scope of bringing IKEv2 to begin with. Because they added IKEv2 to and to fix up some design flows, some insecurities, and of course to also add a lot of other options to make it scalable, flexible, and more secure. Now for the CCNA security, only IKE, which is also known as IKEv1, is in the scope. However, a basic overview of what IKEv2 adds as opposed to IKEv1. So everybody, let's say, agrees that IKEv2 is the new standard, so ideally you should bring up IPsec VPNs using IKEv2 for a lot of reasons. I just added here a couple of them. First of all, negotiation process is shorter and simpler. Negotiation is also more secure. One of the built-in functions in IKEv2 is a real and functional anti-denial of service. So what that does, it means that when the VPN peers, negotiate the IPsec tunnel and they end up with a key material, we need to make sure that this process is not susceptible to denial of service attacks. In IKEv1, that was not built in to begin with. They added a couple of functionalities in there, but it never, let's say, was it was never a bulletproof, let's say, implementation. Also in IKEv2, all messages all control plane messages to bring up the tunnel or tear down the tunnel are sequenced and acknowledged. In IKEv1, that was not part of the standard. Some vendors have added that capability in there. It unifies multiple RFCs into a single one. So in IPsec VPNs with IKEv1 as the key management protocol, we had pretty much like 15-20 RFCs in there, which IKEv2 fixes that, and it brings everything into one common RFC. Of course, additional standards have also been defined, which means we have additional RFCs with IKEv2 as well, but still the main functionality of IKEv2 with IPsec VPNs is now defined, combined into a single RFC. And also additional features have been added, which means in IKEv2 we can have the VPN gateways to authenticate differently. So asymmetric authentication is supported in IKEv2. like in IPv1, both VPN gateways have to run the same authentication method, either pre-shared keys or RSA digital certificates or elliptic curve digital certificates or RSA nonsense. So both of them had to use the same authentication method. In IPv2, because nowadays we want scalability, in IPv2 they change that around, and the VPN gateways can authenticate in between differently. Like one gateway can use pre-shared key authentication, the other gateway can use RSA digital certificates. And also they added IP support, which IP is another framework which is going to be used in remote access VPNs to, let's say, now have a standard method of authenticating the remote users, which in IPv1 it was not standard. Now, how IPsec VPNs works? So it's fundamentally is going to be an IPsec VPN is being built in two main steps. Step number one, which is of course the biggest and most important one, is to actually negotiate a tunnel. So bring up the IPsec VPN tunnel, which is going to be the control plane part. And once the negotiation is successful, then we're going to be able to securely transmit data over the IPsec tunnel. That's going to be the data plane part of the IPsec VPN being built. Now again, just to make sure it's clear for everyone out there, IKE or IPv2, it's going to be only part of the control plane process for the IPsec tunnel, because it's only used to so that it's a framework to define how the negotiation happens and how the VPN peers should end up with the secure keying material to then secure the data plane. So IKE and IPv2 have no, let's say, responsibility in the phase 2, which means actually transmitting data over the IPsec tunnel. Now, IPsec tunnel negotiation with IPv1, of course. So we only speak about IPv1, not IPv2 now. IPsec tunnel negotiation with IPv1 or with IKE happens in multiple phases. We're going to have phase 1. We're going to see what the scope of phase 1 is, and that's a standard phase, which all the vendors supported in the same way. So phase 1 has to be negotiated, has to come up, and then phase 2, which is also standard, has to be negotiated and come up. And once phase 1 and phase 2 are negotiated, we call that the IPsec VPN tunnel from the control plane point of view has been built, and now we can send data securely in the IPsec VPN tunnel. Now phase 1.5, it's only used for remote access VPNs in order to authenticate the user, like via username and password, and for a lot of other reasons. But phase 1.5 was not in IPv1 a standard, which of course created a lot of problems in there with inter-vendor interoperability. So now let's look at those two phases of IPv1, phase 1 and phase 2, and let's see what is the scope of each of those phases and how do they work. So from the control plane point of view, of course, because IKE it's only responsible with the control plane part of negotiating the IPsec VPN tunnel. So first, let's define the scope. The scope of phase 1, the IKE phase 1, is to negotiate a secure transmission channel between the VPN peers. So the scope of phase 1 is that the VPN gateways are going to run some kind of negotiation. They're going to actually send some kind of traffic in clear text. We're going to see exactly what they send in clear text. But then when phase 1 is built successfully, then both sides end up with the same keying material, the same secure keying material that they can use afterwards to send traffic securely in between the VPN peers. So the scope of phase 1 is just to bring up a secure communication channel between the VPN gateways. And there are secure communication, so when phase 1 is up, both sides end up through the Diffie-Hellman exchange with a common shared secret key. And from that common shared secret key, which they don't transmit that over the wire, never, the additional secure keys are derived from that common shared secret key. Now the scope of the additional secure keys is to partially secure phase 1 negotiation and fully secure the phase 2 negotiation. And also, those additional secure keys are going to be used to derive key material for for the data plane, which means traffic being sent to the IPsec tunnel. So to make it clearer, the scope of phase 1 is to negotiate a secure communication channel, which means the VPN gateways end up with the same secure keys without sending them over the wire. So then they're going to use those secure keys to secure the last messages of phase 1 and to secure the negotiation of phase 2. And also they derive keys so that when the IPsec VPN tunnel is up, those additional keys are going to be used for actually securing the traffic being sent through the IPsec tunnel, so the data plane. Like for example, if you look in the RFC, in the IC RFC in 2409, we have what is called the S-key ID, which is that secure common shared secret key, which is only known to the active players in the exchange, which means to the VPN gateways. So through the diffie-Hellman exchange, which we're going to speak about in a couple, both VPN gateways end up with that common shared secret key without ever exchanging that over the wire. And from that secure key, which is the base, they derive additional secure keys. You can look at that key like the master key, the master key or the pre-master key. And then as you can see from that common shared secret key, then both VPN gateways locally they compute additional keys, and those additional keys are going to be used to secure, as I stated, the last portion of the phase 1 negotiation and the phase 2 negotiation, and also secure data plane traffic being sent through the IPsec VPN tunnel once the tunnel comes up. This is more of an advanced topic, but just to give you a better understanding of what happens behind the scenes.